Hi, I'm Gregory Winston from Chicago, Illinois in the USA. This lesson is for week 2 of Introduction to Music Production at Coursera.org. I will be teaching analog to digital conversion using Audacity and Adobe products in my home studio. Sound is pressure variations in the air and is continuously variable. It's not separate discrete steps. The computer can only understand separate discrete steps, numbers, ones, and zeros. There is a process for going from the continuous variations of sound to the discrete numbers used in the computer, and that process is called sampling. I'm going to take my time to say something about binary information, the ones and the zeros, the kind of information that the computer can understand. I'm doing this because how I understand or visualize binary information will control how I understand or visualize analog to digital conversion. The first thing that I'm going to do is talk about binary versus decimal numbers. Think about the number 1 in several different languages. French, un. Spanish, uno. German, ein. They all point to one thing. Names of numbers are always pointing to the number of things. The number 4 has no meaning unless it's pointing to 4 somethings, 4 cars, 4 people, 4 beats, etc. I want you to picture a row of computer monitors. On each monitor you can put one and only one of 10 digits. This is the decimal system that we all know and love. If you display the symbol 3 in the monitor on the far right and zeros in the other 3, then we say that the monitors are pointing to 3 things. If I now put the symbol 2 in the monitor that is second from the right, we say that the monitors are pointing to 23 things. With binary, we are only going to use 2 symbols, 1 and 0. When we put the symbol 1 in the far right bucket and leave the others with zeros in them, we are pointing to one thing. If I put a symbol 1 in the second to the right bucket and leave all the others with zeros in them, it looks like the decimal number 10, and we will name it 10, but we say it's binary and it points to 2 things. If we now put a 1 in the far right bucket of our monitors, it will look like the decimal number 11, and we will name it 11. But we say it's binary 11, and it points to, in decimal, 3 things. Now I'll count 16 things in decimal and show them represented in binary. In this model, we call each monitor a bit. 8 monitors would be a byte. If I then had 3 bytes side by side, that would be 24 bits. Keeping those 3 bytes together for all of our numbers, we'll refer to it as having a 24-bit word length. Let's see how word length is related to amplitude and the sampling rate. To make our visualization simple, we're going to use the 4-bit word that we've been practicing with. We'll flip it on its side and use it to model our sample rate by laying them out side by side. Using our pink sine wave to represent 1/32 of a second of our 512 Hertz tone, we're going to pack 24 of our 4-bit words in at a time frame, or if we multiply it by 32, we'll have 768 samples per second. Just looking at our representation, you can see that we would miss a lot of the shape of the wave. Let's zoom in to see what it would look like to capture one period of that wave at 44,000 times a second. You would have to do that 512 more times to capture 1 second of the 512 Hertz tone. And as shown in the release video, if you change the data to even one of those sample points, we humans can tell the difference. If we go back to our pink wave with our 4-bit word on its side next to it, we can see that we can fit the wave into the 4 bits. But if we increase the amplitude of the wave too much, we can also see that some of the wave would be over the 4 bits, and that part would be chopped off. We would hear that as distortion, and one way to fix that distortion, if we couldn't reduce the amplitude, would be to increase the word length. Well, I have to say that my biggest takeaway is that it takes a lot longer to do this than I thought it would. I learned a lot. Next time I will spend more time creating the lesson.